never used VMs, right? And everybody
Okay, I think we're going to get rolling here. This room is sponsored by Rubicon. The Rubicon project has engineered the Advertising Automation Cloud, one of the largest real-time cloud and big data computing systems. The company's mission is to automate the buying and selling of advertising by offering innovative products to connect buyers and sellers globally. For more information, visit www.rubiconproject.com. We'd like to ask if you have the opportunity to visit the feedback website and fill out a session survey. It's on the back of your badge, or it's on the paper that came with the badge. Okay, our next speaker is Tim Hockin. The subject is Container Management at Google SCaLE. He's going to be discussing the Kubernetes open source project. And so without further ado, I give you Tim.
Thank you. So I've prepared a lot of material. I'm going to try to get to as much of it as I can, but I'm also going to try not to race through. So if any point people feel like I'm skipping over things that are important, please raise your hand and holler, and I'll certainly back up and dig deeper. I think it's important that people ask questions in real time, so if you feel like you've got a question on a slide, jump up and down, make me see you so that we can talk about it right then and there. I think it's easier than doing it at the end. My name is Tim. I'm a senior staff engineer at Google. I've been at Google about 10 years. I've worked on various things. My background is in hardware and BIOS and system bring up. I worked my way up through the operating system and into the cluster. So I come at things from a sort of a unique low-level perspective. We're going to talk about containers today and some of the stuff we do with containers. So first and foremost, containers. I'm going to assume that everybody sort of gets containers, but I'm going to talk about it from Google's perspective. Everybody has a different sense of what it means for containers, right? So in the good old days, we had shared machines, right? And you want to deploy an application, you got some time on your shared server, your admin installed whatever packages you needed. There was no isolation, there was no namespacing. Your app could see any other apps that were running on that server. If you needed a different library than what those applications on the server needed, you were sort of for a world of hurt. And what happens is you end up coupling your applications to the OS, right? How many people are familiar with the apt-get install Apache and then go write out your Apache PHP application, and then you need to upgrade Apache and oh damn, it broke, right? That hurts. So then people started moving to virtual machines. At least in a virtual machine, now I can control everything that I need, right? I've got some isolation. You can't see what I'm doing. I can use my own libraries. I can manage my own applications. But it's expensive. VMs have a lot of overhead. They eat memory, they eat CPU. I think CPU is not too bad these days, but I/O is a big one. And in the end, your application is still very coupled to the OS. It just happens to be the guest OS now, right? So you've chosen, I'm going to deploy my application on CentOS, but you're still highly coupled to CentOS. And if CentOS revs the version of PHP and you need PHP, you're in trouble. And VMs, they're hard to manage, right? You still have things like Puppet and Chef and Salt and Ansible to manage the VM itself. So you still have this high coupling of your application and the OS. So welcome to the new world, containers. Containers give you the chance to focus on your application. Inside a container is your app, your libraries, that's it, right? You don't need to worry about what's on the host OS. You don't need to worry about what other people are doing. You don't have the overhead of running a virtual machine. There's no guest kernel, right? So you don't have all the page translations. You don't have the I/O and buffering in between. But it is not a substitute for virtualization, right? Containers, they do not engage the virtualization hardware. And trust me when I say that Intel has put a lot of energy into making that virtualization hardware really good and really stable and secure. Containers don't give you that. So if you think that containers are a substitute for virtualization, I want to try to correct that idea. Containers are, in a way, better packages, right? They're better RPMs. There's no DLL hell. You package everything with yourself, and you don't have to worry about other people. In a sense, if you squint, they're like very tightly sealed static binaries, right? All the libraries you need are built in. The nice thing about containers is that you get isolation from each other and from your host. You can do resource isolation. You can get user identity isolation. You get file system isolation. You get network isolation. It's very nice. But how do these things work? Containers today are implemented by a handful of sort of very loosely coupled kernel interfaces. There's C groups, control groups, which is a kernel subsystem that lets you define for each sort of resource class, like memory or CPU or network, a group of processes and lump those processes together, and then apply restrictions on that process set as a whole. For any developers out here, the earliest form of C groups, before it was actually called C groups, what we did was we attached a group ID to your process when we started it up, and since you're not running as root, you can't change your own group IDs. And then we would scan over all the processes in the machine, find all the ones that had that group ID, and assume that they were part of the same group. And that's how we did our accounting, right? Doesn't scale so well, so we invented C groups. This was about 2006. And C groups have really taken off, and they've really become a foundation for containers in the world today. The second kernel interface is namespaces. Namespaces are all about changing how you view the system. So a process namespace means that I can only see processes within my shared namespace. And a mount namespace means I can only see file systems that are mounted within my shared namespace. And I can change things within my namespace, and you can't see the things that are in my namespace, and I can't see the things that are in your namespace. We have namespace interfaces now for process IDs, users, mounts, IPC, network. It's actually a very nice system. Capabilities is the third set. Capabilities are a long-established Linux thing that lets you restrict what users can do. For example, you can take away the user's ability to mount file systems or kill other processes, those sorts of things. So you can sort of add or remove capabilities to processes to grant them extra privileges. And then the last and the most simple, probably the oldest, is troots. Changed root, which means this is, for my process, I give a directory and it becomes the root file system for my process. My process cannot escape that root file system. So I can make a directory that has all the files that I want my application to see, and I can change root into that directory, and that's it. They never see what goes on in the root file system. So Google now. Google's been doing containers for 10 years, right? I mentioned how we do process group tracking. Google invented C groups, or at least contributed C groups, back in 2006. We have been doing this fundamentally as a way of sharing our workload for 10 years. Everything at Google, with one little asterisk, runs inside a container. That's Gmail, web search, maps, ads, everything that you've interacted with Google, every product, every Android app that has a Google backend, all run inside containers. All of our MapReduce, all of our batch work, all of our storage, GFS, Colossus, you might have read some of these papers, they're all implemented inside containers. Even Google Compute Engine itself, the VMs that you run on GCE, run inside a container. So Google, we love this stat, 2 billion containers a week. Every week we start 2 billion containers. That's every MapReduce we do, that's every Dremel query we do, that's every search job, that's every Gmail mailbox, everything we do every week, containers. So what is it about containers that made us sort of skip the VM revolution? First of all, there's performance, right? Google's very performance sensitive. At the scale, when you're talking about thousands and thousands of machines, a few % of performance actually really adds up in terms of your expenses. So containers give us really great performance. They give us really great repeatability. This is really important for apps inside Google who want to launch their application. They have to figure out, well, how many copies, how many replicas do they need, how much memory do they need for each application, how much load can they handle under these conditions. They run their benchmarks, they run their tests, and then they deploy. And if what they deploy acts differently than what they tested, we're all in trouble, right? So repeatability is a big deal. In fact, a big trade-off we make all the time is repeatability versus efficiency, right? We'll take repeatability over efficiency every day. So isolation is a huge deal for us. In fact, isolation is the #1 thing that matters to Google about containers. When I say isolation, I really mean performance isolation. I really mean this idea that you and I can share a machine, and there's nothing you can do that will screw me over, right? I can run web search while you're running a MapReduce, and you can't hurt my latency, right? This is the sort of platonic ideal. We're not quite perfect, but we're pretty good. Quality of service. Containers let us give differentiated quality of service so that we can give our batch jobs a lower cost and say, look, you might not actually schedule over a period of, say, 5 minutes. You're still there. You're still running as per the kernel, but we didn't give you any time slices because, Michael Jackson died and we have to serve the web traffic to answer this, right? Because you have a lower quality of service. Accounting is a huge deal. One of the big advantages of running things in containers is I can see with very high fidelity how much memory you used, how many CPU cycles you took, how much disk I/O you did. Those sort of things are really important when we want to go back to our users and either charge them back or just send them an advisory note saying, hey, you're burning through a lot of CPU cycles or you're thrashing a lot of cache pages, those sorts of things. So accounting is a huge deal. Visibility is sort of part of accounting. If we can't see it, we can't measure it, right? And then portability. What this gives us, what containers have given us, is the ability for applications to not think about the machine that they're on, right? For the most part, the people who administer the machines and the people who administer the applications are two different groups of people, and they don't really need to coordinate very much. And it's actually really wonderful. So fundamentally, containers is a new way of looking at applications. Now, enter Docker. Who hasn't heard of Docker, right? I ran this through Google Trends just because I thought it was interesting. Over the last year, you can see, like, holy cow, right? But what is Docker, right? Docker is an implementation of the idea of containers, right? It's sort of easy to conflate Docker with containers and say, well, if you say containers, you must mean Docker, right? And that's not actually true. Docker is an implementation of the idea of containers. It's a good implementation. It made a change, right? Docker really changed the conversation, right? Mad props to those guys for producing something simple, easy to use, easy to approach, that people understand, and that completely pivoted the industry, right? Docker it's a package format, right? It's a way of building up your application, putting it together, and distributing it to other people. But more than that, it's an ecosystem, right? There's all these tools that are building up around Docker. There's all these people and support sites and processes and documentation and books that are being written around Docker. It is also a company, right? So they have some fiduciary responsibility, but they're really focusing on the technology. Mostly it's an open source juggernaut, right? I mean, it's this thing that can't be stopped, and it's fantastic. We love it. We're super happy. The world is finally starting to adopt containers. I was saying just before, the history of Google's experience with containers is we try to do something really clever. We need a kernel patch. So we go out to the upstream kernel maintainers and we say, well, we need this patch to be accepted because it helps us in terms of our isolation. And they go, you're crazy, go away, right? You don't need that. That's too complicated, go away. And there's, we're like, but we're Google. But it didn't matter, right? Now you can go out and say, well, Docker needs this, right? And suddenly the kernel people are like, yeah, well, okay, I guess. So it really has changed the conversation. It's just starting now. I expect to see more and more of this. When you talk to kernel people and you say Docker, they go, oh, Docker. Because it's brought a whole bunch of new requirements that the kernel, this monolithic thing, has tried to ignore, right? Isolation is hard. So we talked about Docker sort of as an implementation of containers. Let me talk real briefly about an alternate implementation of containers. So Google produced something called Let Me Contain That For You. We released it shortly after Docker open sourced in 2013. Not at all intended to be a competition with Docker. It was actually, we released it to try to influence the discussion with the kernel people, right? Really, first and foremost. It's also open source. It is literally the same code that we run inside Google for isolation, right? There's a few things that are like pound if def out, but otherwise it's exactly the same code. And I promise it is not what you want to use. It's more complicated than Docker. It is not nearly as fine-tuned as Docker for the user experience. It's really, really, it's more of a library than a product. Docker is about namespacing. Docker's first concern is about what you can see, right? Resource isolation and performance isolation were really afterthoughts for Docker, and they still really are. You can tell a Docker container CPU limit and memory limit, and that's it, right? And what are those units? Well, they're actually sort of just bleed-throughs from whatever the kernel implements, right? So CPU is indicated in shares. Do you know what a CPU share is? Like it has a technical definition for the kernel, not very useful for users. Let me contain that for you, on the other hand, is all about performance isolation, making sure that your jobs can't hurt each other. We didn't even do namespacing. When we open sourced it, we didn't have support for namespaces at all. We've since added it, but we don't even use it inside Google. We don't use the namespacing part of it. Docker has focused on making things really simple and self-contained and obvious and easy to use, really approachable. The repository, the tooling, everything around it is beautiful. Let me contain that for you, totally ignored that problem. We didn't try to handle packaging. We didn't try to handle images. We're focusing just on isolation. So let's talk about isolation. The core principle of isolation is apps should not be able to hurt each other, no matter what. Anytime that happens, it's an isolation failure. And we get a few times a year people inside Google saying, I did this, and it was running against that, and it hurt me, right? And we consider that a very high priority issue, and we try to figure out what we can do to mitigate performance issues. Every time you run your application, you should see about the same performance. Nothing's ever going to be identical, right? There's always going to be a few escapes, but we want it to be as close as we can. This gives us our graduated quality of service, which lets us make real-time decisions about resourcing and about performance. I'll talk a little bit about what that means in a bit. The main goal with isolation is that it's correct in all instances, but sometimes not optimal, right? The idea here being that at the very bottom of this stack is an autonomic system that controls isolation, right? What that means really is no user space components, or very few user space components, because they can crash. We don't really trust them. So we try to teach the kernel to do what we need as much as we can, and then we take our hands off. Now, the kernel will make correct decisions, but maybe not optimal decisions, right? And then the way we talk about our system is through SLOs, through service level, objective, thank you. Brain freeze. Service level objectives, which is, this is the performance we intend to offer you, right? And so then our users can make their decisions about what they buy from our systems in terms of what those SLOs are. So isolation, let's consider a hypothetical machine with 8 gigs of memory and 4 cores, right? It's a puny little machine. It's probably your phone at this point, right? But it was not so long ago that we were building racks and racks of these. So we schedule a job in here, right? It's sort of sketchy to try to consider this in two-dimensional space because it's not really a two-dimensional problem, but it helps to visualize a little bit. So I drew it as casting shadows in both directions. So you schedule a job, and it fits just fine on the machine. So I schedule another job, and it fits just fine on the machine. But you can see we're getting preciously low on space. So I schedule a third job, and now I'm full. I've used up all the CPU on the machine. I've sold it, right? I cannot resell that CPU. I've guaranteed it to people through their SLOs. What that means here, though, I've stranded a bunch of memory, right? There's nothing I can do to get that memory back because there's no CPU to use it. Memory by itself is not really that useful. So the advantages of isolation, we get this sharing, right? Users don't have to really worry about the noisy neighbors, right? With, again, a little asterisk. We'll come back to that. And it's predictable. It allows us to offer these really strong SLAs to our users, but the downside of it is you have things like stranding. It's confusing. People always ask us, well, how much memory should I buy, right? Well, the analog today is like, what size VM do you buy, right? Do you buy a 4-core or an 8-core VM, right? VMs typically come in a small menu of sizes, whereas containers we offer in sort of arbitrary slices. So one of the things that we really need here is sort of smart auto-scaling. And isolation is expensive, right? The more certainty you want, the more expensive it is. So in reality, the problem that we're looking at, I drew it in 2 dimensions, but in reality it's a multi-dimensional scheduling problem where you've got CPU, memory, disk, network, disk space, and disk throughput are actually different things. Some people consider network to be asymmetric, so you've got input and output bandwidth. Holy cow, that makes for a complicated system, right? And I'm not even talking about all of them. So let's talk about sort of the reality of isolation, right? We've got this thing underneath all of our apps called the kernel, right? And the kernel actually uses some amount of memory and some amount of CPU and some amount of, well, maybe not network bandwidth, but other stuff. We can estimate how much the kernel uses. We can measure it. We can do statistics on it, but we can't actually limit it. I mean, what would it mean to put a limit on the kernel, right? So let's look at this graph again. what you see is the OS uses, a tiny slice, a couple % of your machine, but that third job that we had packed in there, it's gone, right? It's overcommitted. So I have to kick it off the machine. Now, besides the kernel, we also have a bunch of daemons that run the system. We have our node agent that actually manages the jobs. We have init, we have cron, we have all of the stuff that is running on the machine. We do limit those, actually. We run everything, all of the system daemons, we run in a little container called the sys container. And the sys container has a hard limit, and we have set up priorities within the container so that in the case of out-of-memory situation, we know which one to kill. So for example, our node agent is designed to be able to go down and come up without hurting the jobs on the machine. So we make it first to be killed. Hey, because why not? Sacrificial, right? We do limit these, but the failure modes are not great. I mean, if I kill init, you're sort of in trouble, right? But we have to make sure that init doesn't run away with memory, especially if you start thinking of init as something like systemd, which ceases to be 100 lines of code and starts to be 1,000 lines of code. I trust that a lot less, right? So I'm going to put some limits around it. So now you add the sys container, and suddenly that third job is just completely ineligible. It's not even halfway there, right? It doesn't even fit. And now consider a fleet of 1,000 machines, and I'm taking up, say, 200 megabytes for the sys container. Now I need to raise that. I need to add a new system daemon, right? Change it 200 to 250. That's 50,000 megabytes of memory that I'm going to consume out of the fleet that I can no longer schedule to, right? So you sort of see the costs of strong isolation. But the reality is, if anybody in your system is not limited, if they're not constrained, then all of your SLOs are void, right? As soon as there's one guy on the machine who can leak memory and consume everything, everything else that you've tried to guarantee to people is completely gone. We pretend that we can limit the kernel, but only because we have a lot of experience measuring it and monitoring it, and we trust that the kernel doesn't run away. And if it does, there's not much we can do about it, right? Experience has shown that this really does hold up. We'll talk about this a little bit more later, so hold on to this thought. The results of this sort of design of hard isolation is it works really well for the class of jobs we call latency sensitive, right? This is web search, Gmail, ads, really well. They get these really strong guarantees, but there are still some things we can't isolate. Cache right now is sort of the last frontier. Intel has finally given us some hardware that can do cache isolation. It's not great, but it works. We've been begging for this for years. It's right now, not a summer goes by where we don't have an intern who schedules a MapReduce, who runs on 5,000 machines, and that MapReduce chews up all of the cache by just pointer chasing all around memory, and whatever latency sensitive job is on that machine, he goes, hey, what the hell happened, right? Why did my performance go down? And we hunt down that intern and we say, please don't do that, right? And then we try to fix the system to make sure they can't, right? So we have this project we call CPI squared, which is a real-time performance monitoring system, but ex post facto. I'm happy to talk about that later, but I don't think we're going to have time for it. But it's all about noisy neighbor isolation. So then we have some resource dimensions that are just really hard to manage. They're really hard to schedule and isolate. Like disk time is the canonical example of it. There's so little disk time. I mean, can you really comprehend how slow a disk is compared to memory? Like it is so bad, and there's so little bandwidth to schedule that you really cannot effectively schedule it, right? What it means is all of your CPU and all of your memory are stranded all of the time because you're scheduling for disk. So we have some really sort of gratuitous hacks to work around this, and sort of, in some cases, if you use local disk, you're going to have a bad time, right? Then we have the utilization problem. Everybody who runs a cluster of more than a couple machines is familiar with the problem of, why is my utilization 4%, right? The problem is all of these latency-sensitive jobs, they budget for peaks, right? They budget for burst, and they don't use most of their memory, and they're idle most of the time because, Michael Jackson's already died, and they're waiting for Madonna now. And in the meantime, their CPU's idle, right? I love Madonna. So most of the time, their resources are idle. So then you go off to your CTO and you say, well, here's our operating budget for next year. And he says, well, why the hell did it double? Your utilization is 4%. Why don't you just double your utilization, right? So this is tricky, right? This is not a well-tuned system for compute-intensive work like batch. And lastly, users really don't know what to ask for. They do not know how much CPU and memory they really need. Most of them stick their finger in the wind and make a guess, right? And then they never adjust the guess. As long as they don't crash, it's probably good enough, right? So what I've illustrated here is like the reality of difference between what people use versus what they booked, right? And there's all this idle space. So what do we do to make better use of it? This is where we get to graduated quality of service. We resell all of your unused stuff, right? We measure how much memory you're actually using, and we measure say your 5-minute working set. And whatever's not in that working set, we're going to go resell it to somebody else, right? And we're going to give it to them with a lower SLO. It's such a low SLO that they don't even have to pay for it, right? They get it for free. But if you need your memory back, I will shoot them in an instant, right? And so in reality, this is good enough. For the vast majority of batch work, it actually completes. It might not complete right away. It might not complete in this 5-minute stretch, but it will eventually complete. And that's good enough. But there's some shortcomings here, right? There's even more isolation failures here, right? The more people to thrash the cache, more people to sort of stress the system and find ways that we haven't contained isolation or contained performance. And it's really, really important that we don't let this MapReduce hurt web search, right? Or hurt Gmail or hurt ads. And it requires a lot of smarts in the bottom of the stack, right? This is, I mentioned earlier, we teach our kernel to do a lot of this stuff so that user space can take hands off, right? Things like deterministic killing, right? We program the kernel to know the priority of every container on the machine so that if the system goes out of memory, it will kill in the lowest priority first. That's a real trick, and the upstream kernel has sort of said, yeah, you're nuts, go away, we don't want this, right? I'm hoping that over time, as people use Docker and other container systems, and Rocket and whatever, that the kernel people will hear more and more of like, I got an kill and I don't know what the hell happened. Why did you kill my most important job? I wanted you to kill this other guy, right? So anyway, I'm hoping that we can influence the conversation there. So in reality, what we want to do is we want to pack batch into all those open spaces. So let's turn back to Docker. How am I doing on time? Probably halfway, right? Yep. Docker today doesn't handle pretty much any of this, right? Docker handles CPU and memory isolation, and that's about it. And even those, it's sort of totally voluntary, right? If you schedule a container that doesn't specify CPU and memory, you do not have a CPU and memory limit, which goes back to my previous statement about all SLOs are void, right? So this is an obvious area for improvement in the air. I think this is a place where the ecosystem of Docker and containers is going to start to feel the pain. We're already seeing this. People are asking questions about, well, how do I make sure that this job doesn't affect that job, right? But there's a whole lot more to containers than isolation. So I've talked for 20-plus minutes on isolation. So let's talk about other stuff. To make a container ecosystem like Google's, you need scheduling, you need lifecycle management, you need discovery, you need a constituency protocol, you need scale up and scale out, you need auth N and auth Z, authentication authorization. We need monitoring, we need health checking. Internally, we have an enormous ecosystem of tools built up around these things. So let's enter my primary project, which is called Kubernetes. Kubernetes is sort of a cool word. It's the root of governor, and it's also the root of the word cybernetic, which is sort of wasn't intentional, but it's sort of neat. Kubernetes is a container orchestrator. Orchestrator is the word that the container world has sort of settled on for this. We called it a scheduler, but orchestrator is good enough. We run Docker containers. We don't run exclusively Docker containers, except that Docker is the only implementation that we have right now. The Rocket guys are working on an alternate implementation. We support multiple cloud environments. We support Amazon, GCE, Microsoft Azure, Rackspace. We support bare metal environments too. We support different OSs. We support Debian, Fedora, CentOS, CoreOS, Ubuntu now. Yes, as of like last week, Ubuntu. So this is a system that is inspired by and informed by Google's experiences here. It is not our internal system, right? We did not take our internal system, which is like 8 bazillion lines of code, and just drop it on your heads. What we did instead is we started over. We said, let's go back to first principles. Let's look at what the world is doing for open source, because Google and open source parted ways a long time ago in terms of like operating procedure. Let's go back to first principles. Let's talk about how we can build a system that brings to people outside of Google the things that we think make Google really powerful, right? We've inadvertently done a really good job of seeding the industry by hiring people, teaching them all about how to use our internal systems, and then having them leave Google, right? So then they all go to these other companies and they go, damn, I wish I had Borg. And many of them have actually reinvented Borg. in all of its glory. So the point here is to manage applications, not machines, to really take this problem and cut it in two. The machine problem doesn't go away, but it becomes something that application developers don't need to think about. Core design principles of Kubernetes. We like declarative, right? We don't want people sending us a message and hoping that we received it. So it's declarative, so we can rectify everything. We build everything in control loops. We're really focusing on simplicity over performance and over sort of massive feature set. So people ask us, like, why don't you support 10,000 nodes yet, right? Well, 99.99% of people don't need 10,000 nodes, right? We can probably handle 99% of workloads in 100 nodes. Right? Think about all the tech startups out there. How many of them have more than 116 core nodes? Right? That's a lot of compute, right? That's a good enough target for now. We're going to handle more, but you know, it's a good starting place. We focus really a lot on modularity because different people have different needs. So right now we're built on systems like etcd, but at least theoretically, etcd is pluggable. You can take etcd out and replace it with Zookeeper if you want to. Nobody's tried, but if somebody wants to, come talk to me. This is the idea, right? Same with the scheduler. If you really need a smarter scheduler, you can actually just throw away our scheduler and put a new one in. It's literally a process that is separate from the core system. We focus on legacy compatibility, right? We have to meet users where they are. If our solution to your problem is that you need to fix your application, then we failed, right? We're trying to meet people with the applications they've got today. That means figuring out how to make MySQL work in the cloud. This means figuring out how to work with Cassandra and Redis and all the existing open source systems. We're very network centric, right? IPs are cheap and they make the whole thing simpler, so we're just pretty loosey-goosey with IP addresses. This will be a problem for some people, but there's a whole new ecosystem of SDN, of software-defined networking that's emerging on top of Kubernetes. A core principle of the system is we do no grouping, right? Whatever grouping sort of schema you define is immediately wrong because somebody wants something different. Something we learned the very hard way inside Google is if you don't give people ways to group the data they want, what they will do is jam metadata into their name and then parse their name later, right? Which is, oh my God. There's a reason that our name field is 250 characters. So we have no grouping construct. Everything we do for grouping is essentially a select query, right? So you can group arbitrarily. We're big on the cattle and pets metaphor. We didn't invent the metaphor, but I think it's fantastic. It captures the idea better than any I've heard. I'll talk about it in a minute. And we're big on open versus closed, right? We're really focusing on working open source first, open standards. This is the way we're working. There is no part of Kubernetes that is designed behind closed doors. All of our meetings are essentially open. Does everybody know the pets cattle analogy, or should I talk about it? Anybody's not heard it before? A few people? All right. So you have a pet, your dog, Fluffy. You love your pet. You take care of your pet. You know all about his personality. You know what he likes to eat. You know when he's sick because you can tell he's acting differently, right? When your dog is sick, you take him to the vet, right? You nurse them back to health and you take care of them. And if your pet were to die, you're really sad, right? Cattle, on the other hand, if you ever heard of cattle and your cattle gets sick, you're going to try to get it better, but basically you're going to give it some antibiotic shots, and if it doesn't work, you're going to kill it, right? You're going to put it down and you're going to get a new cow. And cows don't have names. They have a tag on their ear that says XYZ123, right? And the herds don't even have names. You have herd 22 and herd 25, and they're just different herds. The way of dealing with VMs traditionally is pets. You know your VM, you know how your VM operates, you know when it's doing bad things because of how it operates, you know when it's not feeling well because of how it's performing, right? Cattle, on the other hand, is this idea that you manage everything in bulk, right? You don't associate specificity or names with anything. So from a high-level design, the Kubernetes system is pretty straightforward. Users have different input methods. They talk to our API server, which talks to our scheduler and back and forth, which farms out work to a fleet of nodes, which are running things we call kubelets. The kubelet is our node agent. So there's a few primary concepts of Kubernetes that I want to introduce. First of all, there's a container, right? So we're just define a container as it's an application, right? Today it's defined as a Docker container. In Rocket Land, it would be defined as an app container. It's one thing that's running. And then we have a pod. A pod is a small group of containers that are built to work together. They're highly coupled. When you schedule one, you have to have the other. The classic example here is like a content syncer, something that'll pull your data down from your CMS and the web server that serves it. It doesn't make sense to pull the data down if you don't have a server, and it doesn't make sense to serve if you don't have the data, right? So these things are highly coupled. An anti-example would be the database and the app front end, right? These two things are actually independent. They can scale independently. They don't need to run on the same machine, so they should be different pods. The next concept to talk about is a controller, which is really, it's just a control loop. Observe, rectify, repeat, right? Is the state that is in the world today what I want it to be? Next concept is a service. It's a terrible overload of the word. I'm sorry. We tried really hard to come up with a better name, and all I could come up with was let me contain that for you. So a service is a set of pods that work together. So the simple way to think of it is think of it as a load balanced set, right? It's a set of backends that are essentially fungible. We have this concept of labels. Labels are arbitrary metadata that you can attach to any primary object in our system, and the counterpart to a label is a selector. And it really is, think of like a select pod where label statement, right? It's not stored in a SQL system, but you can sort of build the analog in your mind. This is how we do grouping. So pods. Pods like a pod of peas or a pod of dolphins or a pod of whales. It's sort of a gift to Docker there. Pods is I like the word because it's short. So a pod is a small group of containers. They're coupled very highly. It is the atom of our cluster scheduling, right? We don't really talk about scheduling a container. You talk about scheduling a pod, right? You don't manage a container. You manage a pod. Things within a pod share namespaces. So they share the network namespace. They can find each other as localhost. They share an IPC namespace today, so they can actually do System 5 semaphores or message queues back and forth. We're waiting for Docker to give us shared PID namespaces, so they can actually signal each other or ptrace each other within a pod, right? But pods are, first and foremost, they're ephemeral. They're mortal, right? Pods can die and they can be replaced, and they are cattle. These are the cattle of our system. Again, the example is a file puller and a web server. So let's talk about networking for a minute because we have to talk about networking. Anybody who's played with Docker has had this wonderful experience of like the networking just works. It's sort of awesome as long as you're on one machine, right? As soon as you want to cross this machine boundary, you end up having to do network translation, and you do host ports and you do mappings, and you got to figure out, well, what host port got assigned to that job over there because I can't know it deterministically because it's dynamic. This is very similar to what we do inside Google. And a lesson that we've taken away from the Google experience is, oh my God, this hurts, right? It permeates everything. It permeates the entire system, the Borg naming service, all of the monitoring dashboards. Every application in the entire system has a -- port flag. The job control language has variable expansions, so it can insert a dynamic port. All of our data gathering systems, it's really painful. So we set up a rule with Kubernetes that all pod IPs are routable. We're not going to use Docker's default 172.1.6 networking. When you create a container on a Kubernetes system, it gets a real IP address that is on the same network as the host of the machine. Pods can all reach each other without any network translation and without any port translations, right? When I talk to your pod, what you see as my source IP is what I see as my source IP. What this means is there's no brokering of port numbers, which sort of massively simplifies scheduling and everything else, right? It massively simplifies service discovery too. How many people actually use SRV records for anything, right? DNS supports SRV records. I can't even tell you how to query an SRV record. I don't know. And I've been a DNS administrator for 20 years. Just never used it. It's just not that important. We just don't use it. We don't need it. We actually do support it, but we don't use it. This is a fundamental requirement. This is probably the number 1 or number 2 question that people who are trying to use Kubernetes run into, that they come onto our IRC channel and say, I can't get it to work. I can't ping my other pods, right? Well, because you haven't satisfied this constraint. This is the model that it has to work in, right? Now, to satisfy this constraint, there's a number of tools that you can use that you can build on. If you have a simple, dumb network, just plain old classic switches, it'll just work, right? if you configure your bridge properly. In the Google Compute Engine environment, we set up some static routes, and it sort of emulates a dumb network. In other network situations, we've got a suite of overlays that you can use. So OVS works. There's a tool from CoreOS called Flannel, which is essentially a really simple overlay network. The guys from Weave are working on an integration. The guys from Calico are working on an integration. So there's at least a handful of solutions that you can use. Flannel is a very simple way of doing it. I've not set up Flannel myself, but I've been told that it's a 3-minute setup. So when you run into this, you need to go look at Flannel. Let's talk about labels. Labels are arbitrary metadata. They really are. You can assign basically anything. You can attach them to any of our API objects. These are generally used to represent identity. These are your identifying marks. So if you think of it as things you might want to select on later, that's what you probably want to set up for your labels. These are the only grouping mechanism in the system. So examples of where we use labels, we have a replication control. The way it decides how many things are in its replica set is through a label. We have the service front end. The way it decides what its backends are is through a label. The capabilities of a node are defined as labels, right? And you can use essentially scheduling constraints are essentially label selectors. So just a quick example of nodes. If I have 4 pods running that are all part of my nifty application, a couple of them are in the dev suite and some of them are in the test suite, some are front end, some are back ends, I can sort of select for them in different ways by just building different queries, right? And now you don't need to jam all your metadata into your name and then parse out your name later, because I can actually let you select however you want. Replication. So one of the primary concepts that Kubernetes encourages is don't think in terms of singletons, think in terms of plural. Everything is plural. Even one is really just a special case of a plural, right? You might need one container today, but you'll eventually need more, right? Because everybody's going to be successful, right? Everybody's startup is going to be the next Google. You're going to need more instances. And so replication control is the way you achieve this. Replication controllers are a really simple control loop that has one job. See how many pods survive, are selected for by this query, and if it's not the number you're supposed to have, start a new one, or kill off an old one, right? And that's it, and it just sits there in this loop, and it does this over and over again. This is a keep alive, right? So if you just have a singleton, and I just want to run one MySQL, replication controller with n equals 1 will do that job. If I want to have 800 copies of Redis, replication controller will also do that, right? It doesn't care what machines your copies have landed on. All it cares about is that when I run this selector, I get 800 responses back. If I get 799, I'm going to go start a new one. So as a simple example, imagine a cluster of 4 nodes, and the default scheduling policy is to spread things around. So I've got my 4 copies, and they're running one each per node. And then there's a big lightning strike, and oh no, that node is just gone. It's dropped off the network. My replication controller can only find 3 copies of my pod. So the first thing it does, start up a new pod, right? Now, it turns out that lightning strike really just brought out the top of rack switch, and once the top of rack switch reboots, that machine comes back, and it's still running that pod, right? Well, oh damn, now I've got 5 copies. I'm just going to go kill one. I don't care which one. I'm going to kill it at random, because replication control has no concept of names or ordinality or index. I'm just going to pick one at random and kill it, right? And then I'm back to 4. This is that observe, rectify, repeat loop. So a service. This is maybe the most complicated concept in Kubernetes, and I hope it's not that complicated. It's a group of pods that work together, that act together. So we define an access policy to this set. Right now, the only policy we support is load balance, but we've been hypothesizing about master election and read-write sharding and those sorts of things. When you declare a service construct in our API, we allocate you a VIP. You get a stable virtual IP address that works within your cluster that will never change, even if the constituency of your service changes, right? You could kill off all the jobs in your service and bring back new ones, and the stable IP address still is there. So as a client, all you need to know is that stable IP address, right? Now we go back to the problem of service discovery. That's a DNS problem, right? So when you create a service, I create you a DNS name that says my nifty service. And as clients, I just need to talk to my nifty service, and it will be arbitrated automatically. Yeah?
So for the VIP, is that modular? Or is that all built in?
The question is the VIP modular? No, right now what we do is we do a distributed IP tables rule. So every node in the cluster creates an IP tables rule that traps that virtual IP address and redirects to a machine local proxy, which then does the constituency protocol. Is it hypothetically pluggable? Hypothetically, yes. We have not tried. Yes. So the follow-up was, F5 integration. Yeah, these are, in a sense, services are really lightweight things that don't really rely on cluster-level service stuff, because F5 doesn't understand our constituency, right? Now, you could easily build something that would reprogram your F5 as the constituency changes, like a read from Kubernetes program F5 sort of thing. Nobody's tried yet. I'd love to see it. I'll help you work on it. So I mentioned that the virtual IP address gets trapped to a local proxy, which then does constituency. A question in the back?
Yeah, you float it through HA.
Do I float the VIP through HA? The VIP is attached to every machine. So whatever node you're on is going to act as the balancer for all of the backends. So think of it as a distributed load balancer, right? So in a sense, you can't really get true round robin because everybody's making independent decisions, but you can get things like affinity. So like once my client is connected to one particular backend, it can stick to that backend. And then when the backend pool changes, all of the balancers we can sort of automatically update. It's actually really cute. I like it. This is great for non-native applications. This goes back to the thing I said earlier. If we ask you to rewrite your application, we've failed, right? This lets you work with, you can pretend that you've got a single backend, and now you can scale out to hundreds or thousands of backends. Hundreds or thousands, not of thousands. Maybe hundreds of thousands. Haven't tried it. A little bit more detail about how services work. We do TCP and UDP. We do it through IP tables right now, bounce it through a user space proxy. We have plans on how to get rid of the user space proxy. We just need hands on keyboards. So status and plans of Kubernetes. We open sourced this less than a year ago at DockerCon 1 in 2014. In 2014, we won the Black Duck Rookie of the Year award, which I felt great about. So did our sibling project called cAdvisor, which I'll actually talk about in a minute. In, I guess, August, we launched Container Engine, which is a hosted version of Kubernetes. Now you can go to Google Compute and click one button and spin up a Kubernetes cluster without having to download the source code and without having to manage it. So go check it out at Container Engine. I think if you sign up for Compute Engine, you get $300 of quota free, which will keep you busy for a long time. We have a public roadmap. Like I said before, we do everything in the open, so our roadmap is public. This is our driving towards 1.0 roadmap. The things you're going to see between now and 1.0 are largely stability, SCaLE, core feature set, making sure that we can handle sort of the web serving workloads that we're really targeting for our 1.0. Once we hit 1.0, you'll start to see the scale go from 100 nodes to 1,000 nodes, right? I mean, we're already sort of most of the way to 1,000 nodes, but we're focusing on 100. You'll see the scale go up. You'll see the workloads that we're targeting expand. You'll see sort of the use cases grow. Yeah. So Kubernetes, I thought I had a slide on this. Kubernetes supports isolation exactly as much as Docker does. Which is to say not very well, right? But we're actively pushing on Docker. I do have a slide on this somewhere. Here we go. We're actively pushing on Docker, bringing some of the ideas that we want to see to Docker. So we've got PRs or issues open for parent C groups, so we can do sort of shared resources, arbitrary group IDs, so we can do different owners, and we can do things like disk quota management, things like in-place updates, so I don't need to kill your container just to add more memory to it. Those sorts of things are going to come. You count on it in the next year. Docker is going to grow all these features, right? And we will, as soon as Docker supports them, we will have them. We're ready for them, right? I wanted to talk a little bit about some of the things we do when you spin up a Kubernetes cluster. By default, when you turn on your Kubernetes cluster, one of your options that you have is, do you want to turn on monitoring? Monitoring comes in two parts, node monitoring and cluster monitoring. If you turn on node monitoring, every machine that we spin up will have we'll install something called cAdvisor, which gathers container stats, and it will spin up, if you turn on cluster monitoring, it will spin up InfluxDB and Grafana and something we call Heapster. And Heapster is sort of the bridge between Kubernetes and Influx. And so it will slurp up all your monitoring, all your stats, how much memory and CPU, things your Docker containers are using, and it will squirt them all off into a database, and then you can look at your monitoring history, right? We also support Google Cloud monitoring, so you can inject it into that too, and I think we also support Google's BigQuery, so you can actually inject it straight into Dremel, which is literally what we do inside Google. When you turn on a cluster, you also have an option to turn on logging. Logging will gather, right now it's just Docker's, whatever Docker logs would give you, so standard out and standard error of your containers. But when you turn it on, we'll spin up a FluentD on each machine. We'll squirt all the logs from FluentD off into Elasticsearch, and then we have a Kibana front end that will let you sort of query those things. Again, it also supports Google Cloud logging system. So you see that it's modular here. Just sort of depending on which version of the pod you choose to run in your cluster, you get a different implementation of it, but the same sort of semantic. Important to note, all of these things are built on public APIs, right? So like our replication controller, our scheduler, our logging, our monitoring, none of them reach behind the curtain, right? They're all through the public interfaces. So I talked about isolation. The biggest thing here, we got to meet people where they are today, right? Isolation is a new territory for most people. And if you present sort of the inefficiencies of isolation to a lot of people, they sort of say, well, it's not worth it, right? I'm used to having a shared VM. I put things into my VM very carefully, and if it crashes, like, well, the whole VM's dead, right? So we're going to have to grow into it. Right? This is a place where the community and documentation and best practices, they're going to emerge. Right.
That's something that becomes very, very, very important. But even companies who scale at maybe 10% of the size, still extremely huge. It's important, but maybe perhaps becomes less critical.
So the question is isolation something that really matters at large scale? Until you're at large scale, right? At smaller scale, it doesn't matter. I mean, sure, right? If you've got 10 machines, it doesn't really matter if your utilization is too low because your operating expenses aren't that high, right? If you've got 100,000 machines, I'll argue that it actually matters a whole lot because utilization of 4% versus 10% at 100,000 machines is enormous, right? That's the sort of thing that makes a difference in red or black in your final balance sheet. I mean, it's something that people are living without today, right? So it's obviously not critical to most people, right? But I really believe that as people adopt containers, they see containers as a way to get higher density, to get more sharing, and to get better utilization, that suddenly they're going to go, oh, but this hurts, right? They don't. I wanted to call the tagline of this slide deck, things you don't know you need, but you do. But the .pubs people said no. You're going to need this, right? As you scale up, it will hurt, right? Already people are asking on the Kubernetes IRC, how do I make sure that my database job lands on a different machine than my serving job because I don't want them to hurt each other, right? Well, I get what you're asking, but you're asking the wrong question, right? The question is, how do I prevent them from hurting each other?
I just want to say, if I was a startup, I'd want to solve it when I was small, so that when that time comes, that's like, I don't want to worry about that when I need to serve my geometric spike or whatever.
Yeah.
For that gap where it's extremely important, but it's maybe not loud.
Sure. Well, so the point was that at the 10,000 node range, like it's right in the middle, right? Yeah. If you've got 10,000 servers and you're living without isolation today and you're getting acceptable utilization, hey, I'm not going to tell you you're doing it wrong, right? If you're getting that, more power to you. But when your CTO says you don't get any new servers next year, but you still have to grow your application, right? Then you're going to start to think about, like, well, how do I better pack, right? How do I set priority between these things so if something goes south, when something goes south, right, that the thing that dies is the thing that I'm okay with dying, right? Who was it who said the difference between something that can't go wrong and something that can go wrong is when something that can't go wrong does go wrong, you can't fix it. This is sort of the fundamental mentality, right? Like, it's not something you are critical crying for today, but I think you're going to need it. We're going to keep pushing on the community and on the tooling and on the ecosystem so that when you do need it, it's there, right? This is a place where Google is really trying to get ahead of the curve on the industry and really push on people. So for all the people out there who use it and you start to experience this pain, come in and +1 all of these isolation requests from Docker and kernel and other things. As a quick example of things we do with advanced isolation features, I mentioned earlier, right, if anybody has no limit, then nobody has a limit, really, or nobody has an SLO, rather. One of the things we do internally is that we use the C group structure to say, for those people who have opted out of being constrained, right, well, they get the leftovers. They get explicitly put in a separate group. So even though they haven't asked for a limit, they're going to get a limit. And their limit is whatever's left on the machine after I've sold things to people who've asked me for a limit, right? This encourages people to ask for a limit, right? We have some policies around how resources work and when you can burst and when you can use things over your limits that, again, we just need to build into the community. Again, the net result here is that we have strong isolation for things like here pod 1 and pod 2, while pod 3 is still able to run and sort of not think about resource isolation, right? And if they have something, if they get an experience that they're unhappy with, well, we have tools to make them be happier, right? We want to have auto-piloting and auto-scaling and these sorts of things. Big goal of Kubernetes and containers, shake things up, right? The world is changing. This is a pivot at the speed of which I haven't seen in my experience, right? I think people are pivoting towards containers faster than they pivoted towards virtualization. It's super exciting, but there's a ton of new concepts. It requires new tools. It requires people to really change the way they build applications and the way they think about stuff. We have a lot of experience, but we know that we can't go out and prescribe how people should do things. So we're trying to listen to the users. We're trying to build a system that the users actually want. In a lot of cases already, we've put stuff into Kubernetes that we would not have done for Google, right? But that are directly the response of what users who want to use the system have asked for. The big deal here, workload portability. We want you to be able to run your job on Google or run your job on Amazon or run your job on-prem and not have to rewrite your application for those different environments, because you can run Kubernetes in all three environments, or n environments. We think really, truly, there's an underserved market for people who want to run some of their work on-prem and some of their work in cloud, right? I want to do all my important data crunching stuff on-prem because bandwidth, and I want to do all my compute stuff in Amazon where it's way more elastic, right? We support Amazon. Go run on Amazon if you need to, right? This is not a play to get people to use Google Compute Engine. It's a play to change the world. That's all. Kubernetes is open source, first and foremost. So if you're interested, come and help. It's written in Go. Go is not so bad. If you know any other language, you can learn Go in a couple of days, really. Come visit us at our website. Come talk to us on IRC. There's always somebody on IRC. We've got somebody on call, every day. So if you've got questions, you can come and ask, and we'll answer them. Other questions I can answer for you folks. I have backup slides. We're sort of out of time, but I'm happy to share more with people.
Can you talk about running Kubernetes on the VM standalone machine rather than running on Mesos? So what are the pros and cons of using Mesos as a backend from Kubernetes?
So the question is, what are the pros and cons of using Mesos as a backend for Kubernetes versus straight up on VMs? Mesos is a very mature scheduler. It's got a very big ecosystem of stuff around it. It does have Kubernetes support, although I haven't used it myself, so I can't say how solid it is. But if you have a Mesos environment, if you're willing to sort of overcome that, the hurdle of getting Mesos and stuff set up, if you've done that, but you like Kubernetes, it's a totally acceptable answer to run Kubernetes as a framework within Mesos, right? No, the Kubernetes scheduler gets out of the way, and the Mesos scheduler takes over. And essentially, you use the Kubernetes API to schedule things into the Mesos core, and the Mesos core will choose which machine to run it on, and there will be a kubelet put on that machine, and you'll get the Kubernetes experience sort of at the front with the user and at the back with the application, and in the middle, who cares, right? But if you don't have the need for Mesos, if you don't have hundreds of machines, you've got 5 machines, like setting up Mesos is sort of hard for 5 machines, right? Kubernetes works just fine at that scale by itself, too. This goes back to simple versus complex. We don't think it's worthwhile to build a really complicated, really smart, 10,000 node capable scheduler because most people don't need it. For those people who do need it, there are really good things like Mesos out there.
So that, obviously you said you haven't touched it, but would that maybe solve that question? You said you guys aren't pushing past 100 at this point.
Yeah.
So while we have a separate scheduler, would that make you think that perhaps it would be more comfortable going to a larger scale, or is that?
The question was about pushing beyond 100 for SCaLE. We have pushed beyond 100. We spun up 1,000 node clusters. It wasn't so pleasant, but it worked, sort of. The focus on 100 is really about prioritization. It's not about, like, we'll never support more than 100. It's really about between now and our 1.0, which we're really hoping is in the next few months, we're not going to focus on 1,000. So plugging in something like the Meso scheduler is a great way. If you need 1,000 nodes right now to get there, we'll eventually support 1,000 nodes, and then we'll have an interesting conversation about like the differences between running it on Mesos versus running it on our native scheduler. There was a question back there. The question is, are pods always contained on a single host? Yes. Pods are always co-located to a single host. Think of it this way. Pods share an IPC namespace. You can't IPC across machines, right? You can't do a semaphore across machines. Boy, that would be cool, though. So if you think about the capabilities of a pod, that helps you build a model of how a pod could be scheduled, right? It shares volumes, right? It shares on-disk storage. It shares process namespace. So like I can't signal across machines, right?
Can I use DFS with Kubernetes, like any Ceph or Gluster stuff?
Can you use distributed file systems like Ceph or Gluster? Sage here? He was here a little bit ago. He was sitting in the back. We were actually discussing this with the Ceph guys just this week. The answer at the moment is no, but only because nobody's done it. I'm desperately waiting for somebody who's got experience with Ceph, Gluster, Flocker, pick your favorite distributed file system, to come along and say, I want to do a Kubernetes integration, help me do it. I'm ready to help with the Kubernetes side, but we don't have anybody who has expertise in those systems. So if somebody were to bring up a set of nodes that all supported Ceph, I'll be right there to help you write the little Kubernetes plugin, which is really about 50 lines of code to make it work.
So I'm thinking of replacing your internal content that for you the infrastructure with Kubernetes itself.
The question is, are we going to replace our internal infrastructure with Kubernetes? Party line is we're not taking requirements from internal Google teams right now. Google is too hard of a customer to have. I pity any startup who Google approaches. But our requirements are just too extreme, right? Our internal systems have thousands of features and knobs and ways to tweak out things. We're just not taking those requirements. They're too complicated. They're too far off in the long tail. Realistically, of course, we're thinking about it, right? We, the Kubernetes team, are the same people who built our internal systems, and we're thinking about how do we make that migration path, and why would we do that? When we do it, it's a multi-year plan, right? So at the moment, the answer is no, right? Yeah. Which one? Yeah, I forget. I said it twice, and I forget what I said. I'm drawing a blank. Hit me afterwards. We'll talk. I want to service as many questions as I can before we get kicked out of the room. Yeah, in the back.
It's a really large scale. What is the sort of relationship and ecosystem between a container scheduler and traditional batch systems like Condor or Borg or something? Is it a plan, or is it to work together to try and get containers to come together to serve the batch? How does that work?
So the question is, how do these things interact with like traditional batch scheduling systems? Truth be told, I'm not actually very familiar with the batch scheduling systems. Internally, we have a different scheduler front end, but we use literally the same core of our internal systems, and I think that's where we're driving with Kubernetes too. There's nothing about the Kubernetes core that makes it ineligible to schedule batch work once we have the differentiated quality of service. But the policies around placement and around lifecycle management are obviously very different for a service than for a batch job, right? So I hope that we can see batch serving systems essentially plug in as schedulers to Kubernetes, take input from users in whatever API they want to do, convert it to our internal system so that we can coordinate, and then schedule away. Security. Containers is... Thanks for your time, guys. Containers are not secure. Full stop. Containers are not a security boundary. Inside Google, we have essentially one large security domain where I assume that my colleagues are not actively attacking me. Now, that doesn't mean I'm going to leave my doors open, but it does mean that I'm not going to build steel reinforced frames, right? Fundamentally, containers are not secure. Containers are new technology that are new kernel interfaces that have had very major security flaws as recently as this year. That our security people part of what they do is sit and wait, right? Let's just let it mature a little bit. When a year goes by without any major CVEs, we'll start to talk about whether containers are secure. But fundamentally, containers use a shared OS, right, at the bottom. And so there are ways to attack other processes, either on purpose or by accident, that I'm not comfortable with, right? So we do not recommend people run multi-tenant, potentially hostile workloads in the same Kubernetes machines, right? Now, I hope that, and I expect that in the next year or two, we will see more pioneering in this space about ways to make containers more secure, to prove that containers are more secure, and to get to a place where you can actually start to multi-tenant these things. We're just not there yet. What about network security? Right now, a Kubernetes cluster is assumed to be a flat network namespace. We had literally just the other day, on Friday, a video call with a bunch of networking people about how do we start to partition network up so that you can't see my services across different namespaces of our cluster. Kubernetes has this concept of a cluster namespace, which is sort of a logical extension of a machine's namespace. Within a cluster namespace, you can only see jobs that were created in that namespace. Seems like an obvious place to draw a really hard edge, right, and put a firewall at those edges. So we had this discussion about how to make that happen, like literally just this week.
So if Google isn't going to be using Kubernetes, well, what assurance do we have that it's not going to abandon it?
What assurance do we have that it won't abandon it? I mean, I can't say that we have a great track record. I have felt the pain, reader. What assurances? This is it. This is Google's play, right? Look at the cloud space, right? Google isn't number one. It's not even number two, right? You can argue whether it's number three or not. Fundamentally, VMs for us will always be a catch-up game, right? We're following what the industry has wanted with VMs, but we're so far behind in terms of just like table stakes stuff that it's hard to ever catch up. But we see this pivot in the industry, and we say, hey, we know how to do that, right? In some way, like I have a crystal ball, right? I can tell you what you're going to need 3 years from now, right? And it might be a year and a half instead of 3, but I know sort of the things you're going to ask for, right? This is a chance for us to get out ahead in front. Google has invested massively in our cloud product space and our cloud team. I don't want to talk about internal stuff, but let's just say there's been a lot of reorgs. What assurances can I give you? I mean, it's a massive product play. We really believe that if people experience workload portability and that it's actually, if we make it easy for people to sort of take their work and uproot it from their environment and move it from on-prem to cloud, that when you go look at the cloud providers, you're going to look at Google more seriously. Today, it's just a very difficult proposition, right? So again, I'm not sure what sort of assurances I can make you, except that for example, our team has grown from 4 to 30 plus in a year. Like every all-hands meeting we've had in our organization, the first 5 minutes is talking about Kubernetes. Google takes it very, very seriously. It's not an insurance, but I'm not sure what assurance I could ever offer you. Short of a $1 billion revenue stream, right? Well, and in the end, it is open source, right? You can take it and run away if you want, right? It's all Apache licensed. The whole thing, literally what we run with Container Engine is open source. We actually work on Container Engine out in the open, right? So one of the cloud providers is Container Engine. Like we don't even hide the details of how that works, right? We don't hide our roadmap there, yeah.
So coming from my little pet containers, my little composing wiring together, and my keyboard there, I was a little unclear on the concept of scheduling. Right? So I was wondering if you have a 1 to 10 or something that could describe that kind of scheduling.
The question is, given some pet wiring, how do you?
That's what I mean, not the Google scale.
Sure. So for somebody who's got the smaller scale, who's played with Docker and links and those sorts of things, like how do you go to scheduling, right? So erase the idea of a machine from your mind, right? Pretend there are no machines. There's just a pool of CPUs available. When you want to run your web app and your MySQL, right? You don't need to care what machines they're on because there's no tight coupling between them. So you schedule it. You say, dear Kubernetes, I'd like you to run this job and I'd like you to run that job, right? Kubernetes will figure out where to put them. And if that machine goes away, it'll move it to another machine, right? And if that machine goes away, it'll move it to another machine. And it'll just keep these things going. If it crashes, it'll restart it, right? It'll gather all the stats and all these other things for you. Now, what happened to links? How do I find each other, right? This is where the concept of service comes in, right? So I create a pod that says, application equals, my database. And then I create a service that says, for all pods who claim to be my database, create a front end with a VIP for those things, right? And for that VIP, call it MySQL and create a DNS name for MySQL. Now, my other application just does a DNS lookup of MySQL. It gets this virtual IP address, which automatically finds your MySQL backend. So wherever your MySQL backend moves, that virtual IP address will track it, right? In a sense, you've got what Lynx has given you, except now you can take your MySQL backend and move it across machines. You can take your MySQL backend and change its IP address, which you can't do with Lynx. You can take your MySQL database and replicate it. I mean, MySQL is not so great at replication, but imagine something that was. And so you're freed from this concept of being on a single machine. But if you do have one machine, it still works. I can literally run a Kubernetes cluster on my laptop and schedule onto my laptop just as if I was in a cluster, right? This is sort of the Docker promise, right? This is the thing that Docker did so right, that they got the tooling. So we're going to ape that a little bit, right? It has to be possible to build a dev environment on your laptop, sitting on a plane, completely disconnected from everything, build your application while you're flying to Tokyo, get there and do a demo, right? Yes?
Basically, talk about running containers in the past, on the host machine. So how do you get secrets in the container?
1 second. For everybody who's taking off, I have stickers up here too, if anybody wants stickers. So they're here. The question was, how do you get secrets and things into pods? Funny you ask that, because literally this week was committed a secrets infrastructure. So you can create API objects that contain your secrets, and then you can create a volume of type secret, and Kubernetes will automatically take those secrets from the API, write them into files for you, and map them into your application. So like your SSH keys or your Docker config.
What is stopping for manager pods accessing your secrets?
Again, go back to the security domains, right? So we sort of assume that there's some security domains. Now, we are building auth and an authz stuff to attach to various objects within the cluster. That's not quite done yet, but before long you will be able to say, I've created my secrets object and only users in this identity group can access my secret object, right?
When is that coming out?
It's in development now. I mean, a lot of the authorization plugins are there, but I don't think the full tie-in is done. But it's all being done in the open. The Red Hat guys and the Google guys are working on it. Other questions? Mob for stickers. Awesome.